Thank you very much for the invitation. I'm really glad to be here because it was before the COVID we were planning this trip. And I had already the administration prepared, and it was announced that the orders would be long, and our first paper was with referees back in the day. Now it's already published. But this is the first time in my life when I meet people whom I have papers together with, but we haven't yet met. So it's maybe just to conclude with the off-topic part, I think that I explained that my family came from Chinese, it's a village between Bielsko, Biała and Krakow. My grandpa was a Polish citizen, but unfortunately he didn't teach my father Polish, so my Polish is poor. I understand a bit of Polish and I speak fluent Slovak for various reasons. So I can't give this lecture in Polish, unfortunately. My daughters are learning Polish, so it will return to the family nonetheless. But it's especially a great pleasure for me to be here, pretty close to the location where my family originated from and give a scientific talk. So it's really an honor.
How do you pronounce your surname? Pronounce Koniorczyk.
Koniorczyk.
My name is Koniorczyk.
Yeah. So this is well, we are Urals as far as I know. And in fact, it's very nice that everybody can spell my name here because to live with Polish name in Hungary, that's a challenge. Anyway, so this is what I'm planning to talk about. Essentially, I decided to give a kind of subjective summary of the techniques we encounter around quadratic unconstrained binary optimization. Just a quick and not obviously not very detailed overview of the typical armamentary of various communities they have to attack this very problem. And the problem is the same, and this is pretty much the problem that the quantum annealer is supposed to be able to solve. I say sorry in advance to the experts of various fields. Okay, so obviously, for instance, I will not. So the first mistake is found. I meant tensor networks. Well, I will talk a little bit about matrix product state, though. And obviously, I'm not the right person to be asked about it because you have Bartek here. So I'm not an expert on matrix product states. I'm a fan of these techniques. But if somebody is here who is not too much into matrix product states, for instance, then I think that I will give a clue on what the whole deal goes about. And this is my ambition with all the rest of the first part. And then I will give a brief summary of what we have achieved together so far and about the plans from my own perspective in a way. I try to identify certain scientific gaps which I expect that we will be able to fill in the near future. Okay, so let me start from this problem. Essentially, quadratic binary optimization problem can be always considered equivalently as a maximum cut problem. So you have a weighted graph, undirected weighted graph, and the task is to split the graph into two parts, so that those edges which originate from one of the parts and end in the other part, if I sum up the weights of all these, this should be maximal within the graph. There are some complexity theory stuff here, but I skip these because this is a dangerous field in a way, especially if there is someone who's a real expert of completeness, then I can receive hard questions. So let's summarize those two lines as these are really hard. This is a hard problem and universal enough. Okay, and the classical approach to this problem from the operations research direction, there was an important result by Burmans and Williamson in 1995, and they themselves claim that their algorithm is the first substantial progress in approximating max cut in the last 20 years. That was in '95. And indeed, something started there. So by a raw approximation, we mean that in expected value, we find rho times the optimum. Okay, and altogether about max cut or QUBO, there are a lot of approximations around in the classical literature, of which, to my experience, the quantum community is not always aware of. Now, I don't want to go to too much of details of these approximations, even though they're interesting and evolved. I just quote this famous result of the Goemans-Williams on paper about the approximation. But rather, I would talk about the key tool of the classical approach, which is the semi-definite relaxation, and also the Goeman-Williamson algorithm, how it works. We have this max cut problem. Observe that the variables are -1, +1, but altogether this is a quadratic binary optimization problem equivalently. And okay, at some point this is subject to. I just realized that I forgot to replace the Hungarian version, so this FH is subject to. So this is the original problem, and then we can make a relaxation stating that essentially this V, let's have this VI in the unit sphere instead. And that's a good relaxation. And then the idea is that we solve this one somehow. This is a semi-definite program. Now, semi-definite programs, I will mention them frequently. The problem with them is that there are very nice interior point methods to solve them, but the size for which they work is limited. So from in the classical branch of QUBO solvers, the main challenge is typically how to somehow do tricks to the semi-definite relaxation so that bigger sizes can be solved too. And here we can see that so essentially it's solved. Then there is a random direction wrong with uniform distribution, which is considered as a normal of a hyperplane, and then there is a cut made with this condition, and essentially this is the way how to obtain this Goemans-Williamson approximation. So the important element for us here is the semi-definite relaxation. I will return to this one. Now, QUBO, I suppose everybody knows this, but if eventually somebody doesn't, now I switched from -1, +1 variables to 0, 1. Essentially that's different. They have this quadratic form. Q can be arbitrary, but without loss of generality, I can assume it to be symmetric or upper triangular if you wish. And this is the very problem which we want to solve. And if we could solve it, that would be very effective in general. Then we could solve a heck of a lot of problems, including those linear combinatorial optimization problems for which there are many applications. So currently, the situation with this QUBO, in my view, is similar to when in the 60s the simplex algorithm was invented, and then essentially the operational research community got a tool into their hands. They elaborated on many modeling techniques. It became very prevalent. Now, we might maybe expect a similar breakthrough with QUBOs, provided that classical solutions as well as quantum hardware will achieve such a breakthrough that it really can become a working thing. And about constraints, by the way, so since the QUBO is an unconstrained problem, the way to treat constraints which are there in practical problem is to use penalties. Now the problematic part of using penalties is that you have a multiplier in front of the penalty function, how big this multiplier should be. Obviously it should separate between feasible and not feasible solutions on one hand. On the other hand, it should not be too big, because we are in a finite range. In classical operations research, it's also a typical thing that if somebody uses penalty methods, then it's important how the penalties are chosen, because even in classical algorithms, it can make the algorithm unstable if the penalties are chosen wrong. However, there is a recent result about it, which is also not so prevalently known, that if you have a quadratic problem, as long as the constraints are linear, actually you can find exactly this P. So there is a method written down in this very paper to exactly find the right P, which is good news for those who have linear constraints. Right, now let me go to the first classical approach on how to solve a QUBO, which will work for sparse QUBOs quite neatly. And essentially, we will turn the QUBO into a linear mixed integer program. We will introduce at most this number, so n over 2 auxiliary variables, which are actually continuous. And this is the first paper where I saw this approach. This is again something which is not prevalently known in the community. That in 1960, actually this was found out. And that's the way. Okay. So simply we have the original problem. We introduce these W's. We introduce certain tricky constraints to make it working properly, and we have another objective function. Now, if somebody is interested, with my PhD students, we made an implementation for GLPK, which will be a part of the official examples of GLPK. So if you have a QUBO, you can readily try this with GLPK or with CPLEX, because it's easy to convert our script to CPLEX. So it readily works, and actually it's quite instructive to see how many cutting planes it will use.
Excuse me, so this W is just representing the variable which is a product of xi times xj, yes?
In a way, yes.
Okay, because under this constraint it should be equal to a product of this binary.
Yeah,
yes? Okay.
Definitely. So this is a simple trick.
Yes,
Not a big deal yet. Yet useful. So this is a way how to solve it. Obviously, it will fail in case of huge ones. Now, let us look for another linearization, which, on the other hand, is the typical one used in both the approximations and in the classical solvers for high-performance computers and etc. And it's a very nice description about this in a paper by Nesterov. Actually, Nesterov is right now in Budapest, so if I were not here, I would take part in a course Nesterov is giving. So if you have, but I have a spy there actually, so my PhD student is attending. Nesterov has very interesting results, also in case of quadratic optimization. And this is the trick. I think that the hands of Lovas are also in this story. And what we do is that we introduce this point-by-point inner product. And having this inner product, we observe that essentially we can write the objective of the QUBO in the form of this this very form, where this is this random projector. Okay, and then we have a linear objective, and we have a constraint here that this xxt should be in the convex combination of these matrices. Okay, now this is a constraint not easy to deal with. However, this is at least a linear constraint problem. And now we are in the position to come up with a semi-definite bound. Okay, so instead of having this complex constraint, we just prescribe that this capital X should be a positive semi-definite. And also, since we are dealing with 0-1 variables, we prescribe that the main diagonal should contain zeros and ones.
Yeah, but in this case, you actually allowing the solutions not to be projector, yes, but should be like
Yeah.
any matrix with zeros
Yeah,
and ones.
so it's a relaxation.
Yeah, okay.
Nevertheless, it would be good in a branch and bound for bounding.
Yes.
Especially, it would be very nice if it was so big as the is, which we cannot, right? Okay, so there are some comments about it here, but essentially this is the main technique behind most classical algorithms. I probably skip this part simply. And I switched to these particular classical solvers I wanted to mention after. So now we are familiar with the basic idea of what they're built on. But just a few comments that what I'm telling about here is just the top of the iceberg, because there are a heck of a lot of heuristics around too. There are reviews about them and etc. I mostly focus here on exact solvers. It makes a difference whether they address sparse or non-sparse QUBOs. Sparse QUBOs are typically easier to solve, even though it's I think a rather complex question: what makes a QUBO really hard? And I think that it's not fully systematically understood, because like from a quantum perspective, I would consider a QUBO as hard if, for instance, it's hard to embed, or if the ground state is very frustrated, right? Whereas an operations researcher would say that the QUBO is complex if it generates in the algorithm a lot of cutting planes, and the cutting planes are close to parallel. This is probably related effect, but so there is still there are a lot of things to understand about it, in my view. Nevertheless, I also have to mention that the commercial classical solvers do improve a lot. So there is a paper about a specific solver called MADAM, and I will tell about MADAM soon. And this was benchmarked against Gurobi. The paper was published, but 1 year later, Gurobi was outperforming MADAM. So probably the classical solver producers also realize the relevance of QUBO. There is a big competition in solving QUBOs. Right. So let's just have a quick impression of how these high performance solvers work. This is a relatively recent one. And actually, with Professor Povok, I'm just about to start collaborating. So this means that and obviously, since we are collaborating too, it's a channel towards this field directly. And actually, the very trick they do is that if you just get back this level of the vertex cut problem. Okay. Now they want to help the SDP with certain cuts or simplifications to become slower. So the basic idea of the solver is that let's have a branch and bound with the SDP relaxation in the bounding. But it would be too big. And then what they come up with is that they take this graph picture of the vertex cut and observe that, for instance, if you have a triangle in a graph, then a cut can cross a triangle only 0 or 2 times. And you can make similar claims to bigger odd cycles. And these odd cycle cuts, they help in making the SDP tractable. And this is how the devil in the details. All these solvers have very neat little solutions. I just want to present the main idea. It works, it's available for free. One can upload problems to get solved, and even we can, I can ask for an interface or even the whole code. Yeah, they use further reduction techniques and actually they have branch and cut at the end, I think. Anyway, so this is one recent solver, and I mentioned another solver from this paper. I saw this result in the European Operations Research Conference this summer. And actually one of the authors, I think the first one, gave the talk, explicitly said that people should look at our solver before spending a lot of money for DWave access in a way. By no means I mean I agree. I'm just mentioning this because this reflects the attitude to quantum methods of the operations research community, but I will return to this question. Nevertheless, what these guys did is really a good job because they made a high performance computing solution, highly parallel. Essentially, the idea is similar. They also consider these odd cycle cuts, but they rely also on another linearization based on cycles. So here the variables are not assigned to the nodes, but to the edges of the graph. And well, I wouldn't go into details. You can find it in their paper. Nonetheless, they also employ a lot of tricks. It's a very recent solver, and their intention was to come up with the best possible high-performance computing solver along these lines. Of course, this is a competition. Nonetheless, what they were doing is really convincing. There are a lot of nice reduction techniques written down there. This is mainly for sparse solvers. Yeah, and now, then let me, so just a small break, that this is what I wanted to tell about the classical approaches, and typically the keywords are probably linearizations, semi-definite relaxations, and approximations, which are there in the classical literature, and which probably have a lot of elements interesting for the quantum community too. Now let me switch to quantum quickly. So I was assuming that since people are dealing with quantum stuff here, probably this is more or less trivial. What we do is that we have the Ising model, which is known to be equivalent to the QUBO, and then we turn it into a quantum Ising system, which looks like a crazy idea. So instead of having binary vectors, we start to have a Hilbert space with an exponentially growing size. Nevertheless, this is realized by nature, and what we expect that the quantum devices realize that. So the intention originally is not to have a technique for digital computers, but to have a device which inherently works like that. So another question that actually, since these quantum systems are interesting in physics, and there have been a lot of effort in understanding them, and especially calculating their ground states. The very elaborate techniques of calculating spin system ground states should be fruitful from the operations research point of view. So now, and one of the interesting, so one of the maybe most striking techniques in finding the ground state of a spin system is this matrix product states, or more generally tensor networks. I personally regard it as one of the biggest successes of quantum information so far. Because, so what was the story? The story was that there was a technique in solid state physics called density matrix renormalization group method. It's one of the leading techniques of numerical solid state physics, and the idea behind was that, okay, we are looking for a single state in a huge Hilbert space. Now obviously, this is just one state. So if we eventually manage to split the space into two, saying that it's likely that the space we are looking for is in one of the subspaces, and we repeat this, And finally, we may end up in a small, in a very small, in a reasonably small space where we can already find the ground state, right? Because otherwise, the ground state which we're looking for, it spans a one-dimensional space, right? So we can get close to it. And how DMRG worked is it was a rather heuristic way of splitting the space. Roughly, the idea was that they had split it into two, separated one spin from both. It was mostly for spin chains, and they did some calculations, but there were two problems. On one hand, it was not really clear what the mathematics behind why it works. The other problem was that they couldn't deal with cyclic boundary conditions, which is quite common in spin chains. We prefer like cyclic boundaries, and DMRG broke down with cyclic boundaries. And then it was realized that actually this is equivalent to a variational method on a certain set of variational states. Namely, there are two ways of understanding matrix product states, I believe. One is that if I take a product state, right? So this is this would be a product state of a multi-spin system. I just have coefficients. Now, it's possible to generalize this one in a way that instead of the coefficients, I introduce square matrices, one square matrix for each basis element on each spin, and I parameterize my coefficients like this, which means that here I have products purely. Now this will be not products, but there can be some entanglement represented here already with this one. Now, the very nice way to understand what the heck is going on here, and this is very much quantum information stuff, is that this represents a sequence of entanglement swappings, essentially. So the interpretation is as follows, that you introduce auxiliary quantum systems of a bigger dimension, the dimension being related to the matrix size here, okay? And you assume this dashed lines here belong to singlet pairs, okay, or maximally entangled pairs of these auxiliary systems. So there is a strong entanglement along these dashed lines. And importantly, you connect the first and the last one, to thereby achieving the periodic boundary condition. Actually, if you are to describe a translationally invariant system like a spin chain, then there is enough to have two of these matrices. Okay, so just ignore the upper index here in a translationally invariant case. That's the simplest. Then you have two matrices. What do these matrices represent? They represent the projection from the virtual system space to the real system space, from which it's quite clear that the bigger these matrices are, the longer the correlations are that can be modeled. And what was proven back in the day, I was lucky enough to be there when this paper was published, and it was the time when I met Frank Verstappen personally. They were like correcting the proofs of this one. So ever since I'm a fan of this whole method, because come on, you have a big spin system, if translationally invariant, you describe it with a matrix. Obviously this is an approximation in a correlation line, but come on, around phase transitions, DMRG breaks down too. Clearly this also breaks down. You have what? If you go with the size of these matrices to infinity, and it was actually proven that you get a dense basis in this Hilbert space. And since this is a separable Hilbert space, it means that you can arbitrarily approximate any state in the Hilbert space with that. So after all, at least in case of a spin chain, this is an exact variational method. And when I cut these auxiliary space dimension, I just reduce the modelable correlations. And this became a revolution in the DMRG community. And it's definitely a quantum information idea, like entanglement swappings in a way. It's a success story. And very luckily, if you come here, then we can meet experts of these techniques. And so because we don't have a chain, we have an arbitrary topology if I look at the QUBO, right? But these methods are applicable, and if somebody wants to know how, then one can ask about that. More importantly, it's a very pleasant experiment, but I know some people who are into these. In our institute, okay, if I walk down the corridor, I will meet Örs Legezor, who is also an important player in the MRG and stuff, and is very smart. But it's typically very hard to convince these people not to solve your optimization problem, which doesn't bear physical relevance. It was for the first time that actually I had this experience that Bartek and his colleagues were ready to really solve our minor problems in railways, and this is very good. Okay. And okay. Now I'm just checking because so far this is about digital computers, but I postponed the conclusions to the scientific gaps here. Let me switch now to the physical device, the quantum annealer. This is a very ambiguous thing. Many people have many opinions about that, and many things are not certain. For sure, there is one called DWave, which is available. On the other hand, jolly expensive and not researcher friendly, with this respect. Okay, since there is a camera recording, I will make more remarks on that. Maybe afterwards also I can these devices are getting bigger. Definitely, there is a heck a lot of money pushed into their development. Of course, they are improving, but they are facing problems because the noise is there, and it's probably a fundamental thing which cannot be. There will be no not noisy DWave. With the size, it has to increase. There's also a problem that we don't know the annealing time in advance. I will have a remark on it further. And the embedding, I will also have a remark on that. And there are these hybrid solvers also offered by DWave, but those offered by DWave are mostly black boxes. You will not know what happened, how they found the solutions. If I were evil, I would say that maybe they have just put the supercomputer with a good classical solver behind, and they just give you the answer.
To be honest, you can always inspect the source code. I think it's open source.
Is it or it is?
I think so. It's always been.
I don't know if hybrid is open source exactly.
Oh, okay.
Okay, if you can give it to me, I didn't. It might be my fault, but nevertheless, I didn't find too much of information.
But I think it's just a taboo search combined
Yes,
with
some kind of
so
taboo search, yeah.
of course, the details matters, but it's probably nothing sophisticated.
I would expect so either. So now with quantum, there is a problem that probably all of you know, that the device itself is a fixed topology, whereas your QUBO, it has a different graph, and you have to embed it as a new subgraph of this fixed topology, which means that eventually might be impossible. You might have to link together physical qubits to be able to do that, becoming one logical qubit. I mean, this figure coming from a paper, it's like this pair belongs to that qubit, so the same color pairs represent a single logical qubit, and embedding itself, it's a hard problem actually. So this is something which one has to cope with and dealing with DWave. And this is the annealing time story. That from the theory of quantum adiabatic time evolution. Actually, here there is the noiseless approach, but the similar theory applies to noisy systems. So you can have a master equation for the adiabatic evolution. Nevertheless, typically, of course, I omitted here important conditions, but typically what happens is that the required annealing time depends on the gap between the ground state and the first excited state, which we don't know. Because because if we were aware of that, then we wouldn't try using DWave to find it. So one has to make an educated guess, and one has to try somehow to find out this. This is also a kind of shortcoming. Now, so using DWave, it's I think that it's something which we should do. I personally believe that DWave will find its place in optimization, and we can contribute to this progress. But it's not a battle process yet, using these techniques. Even if DWave tries to sell it as an industrially completely mature and very valuable thing already, I think it will be. We have to work on that more. Now, other gaps, yeah. So there's one thing that there is the physics community who views these whole things from the point of view of quantum systems, tensor networks, and so on. And there is the community of operations research. And so far, the communication, according to my experience, is rather limited.
To say the least.
Hmm?
To say the least. I would say that, yeah, I would say there is a tension between quantum and OR community.
Even there is a tension, yes. So the OR approach is that they don't take us seriously. For instance, this year there was an initiative in the European Operational Research, because they use the British form, so European Operational Research Society, there was an initiative to have a quantum optimization working group. And actually it was rejected. And what the leaders said, that you should show some results first. So they're skeptical in a way. It's also true that I met people from the OR community who were there in trying to form this thing. And okay, again, it's being recorded, so I can tell the details later on. But let me put it this way: that if these guys try to sell what they are doing as if that was quantum optimization, I wouldn't agree to create a working group for that as well. And so it's a responsibility too, because they as like our background in operations research is not as deep as those who've been doing that since the kindergarten. We can't expect them to know as much about quantum systems as we do, who have been doing that for our whole life, right? So there should be respect and interest, and I can say counter examples that there are good operations researchers who are definitely interested in this direction. So nevertheless, there is a lot to improve on the relation between these communities, and I think that it could be a constructive interference. I think we can learn from each other, and this can be of benefit. I hope so I try to illustrate this with the first part of the talk, that there is on both sides there are very elaborate techniques, essentially for the same problem from a completely different perspective. Now, the other thing is that whether we have real applications of, say, quantum techniques versus benchmarking problems. So it is also something that if DWave is affordable, and we can show up certain examples which are really practical, so it's not only like we constructed a problem which is hard and we managed to solve it, but it's in some kind of real application, then of course it will improve on the acceptance, especially in the OR community. Because, for instance, in transportation optimization, like railways, which we've been doing, that's a big field in optimization, like railway optimization. And the expert of that, essentially they're only interested in whether you can solve the problem better than it was solved before or not. And if you can't say that my algorithm or my approach is better than what we did like 2 years ago in C++, they will just not consider it as a result.
I mean, I think the biggest pushback I experienced personally dealing with the OR community was that they don't even accept QUBO as a valid representation. I think they just want to use traditional methods which are not QUBO, and that's the problem, right? So using quantum angular or any other solver that actually uses QUBO representation, it's a higher order problem, I would say. The first order is just accepting the QUBO is a valid representation. Okay.
Even what you say, I think it's an even higher order problem in general in scientific communities and publications. But if there is a research direction and you come up with a really different idea within that research direction, then usually the representative of that research direction, which typically are the reviewers of your paper, they are not very fond of it because it takes them more work to understand what you're doing, and if it's really it's not so much striking to them, or not the next step in a direction they would be keen on going for quite a while, then they will reject it. I have a very representative story about that, but I don't want to take all your time. Later on I can explain, but eventually, so briefly, I have a paper which was cited by Chuang, you know the Nielsen and Chuang book, so this Chuang, and by Ellen W. Oppenheim. If somebody is interested in signal processing, then probably knows his name. He's a very important professor at MIT. And even he wrote us a letter asking why there is no continuation of this research of ours, because it's so interesting. Even they published a paper in which they generalized the results. And actually we couldn't publish that result in a reasonable quantum information journal, because all the referees said, well, we were doing something which was definitely not a technique which was not used before in this context. And the reply was that you're not doing new physics. No.
That's the problem. If you have someone from quantum as a referee, they're going to say that, you know, OR is not the research, not important. And on the other hand, if you get something from OR, they're going to say, well, quantum doesn't work, so why should we use it, right?
Yeah,
so it's kind of limbo.
So I myself, okay, this we can discuss. Now I'm probably
just enter, just push enter.
So, indeed, and we should not give up, I believe, in spite of that, because at the end of the day, I believe that this is an important direction and it should be accepted by these communities. And what we are doing is important, even though they don't realize it. And like in the case I told, it was finally published in Journal of Russian Laser Research, that result of us, which is not a very, it's the journal of the Lebedev Institute, and the only reason why I sent it there finally is that because I knew the editor very well. She was a good friend of my PhD supervisor, and I knew that they will publish, and all what I wanted to see is the paper imprinted. Now I'm not sure how many papers from Journal of Russian Laser Research were cited by Chuang and Ellen Oppenheim, but I believe at the end of the day I was right. Even though we had like 5 turns with the manuscript, and everybody almost said the same experience that we had. Yeah. So, and then digital versus quantum hardware. Obviously, the digital hardware is very elaborate. There are fans of digital hardware. We should somehow convince them that quantum hardware should be interesting. Now, I'm approaching to the end of the talk. I'm sorry, I'm maybe over time. Okay, so very briefly, what we achieved so far. So this is this was an idea. The idea was that DWave as a probabilistic solver, it will return you a statistical sample, which in the lucky case it contains the optimum. And the idea was that if we make some assumptions based on some physical model of the device, we make some assumptions on how this distribution should look like, then hopefully from that assumption we can come up with statistical methods, we can come up with a discriminator which is not certain, of course, it might fail, but it can contribute with an estimate of whether we have sampled the optimum or not. Now, we found that in certain instances it learned. We thought that the idea is interesting, the referees agreed in that. We have the code, definitely to proceed with this we need more calculation, more samples and more experience with this discriminator. But this is a paper we have published, and I personally like this result. This was one of the, I'm not going chronological order, it was the side effect of the lengthy project we were doing. Now that railways come into picture, so okay, apart from being rail fans, both of us, I appreciate. So the whole thing started like I met Christian Domino, and it turned out that actually both of us are interested in railways. Moreover, both of us worked for in a particular railway environment. I was an employee for a while of a software company doing software for passenger rail transportation. My field was crew scheduling and rostering, and I was doing some optimization too. Even I have some papers about that, the most prestigious one being in transportation research at sea. So I had a bit of an experience with railway operations research. In fact, I was making my money for a while from this. And then there was Christian Domino, and he also was an employee of a railway company, and as you can see, we are very much fond of this. Right? Before anyone claims, so this, I'm not driving this DMU, this goes to the opposite direction of this, I'm just sitting there, because there is a recording now if some railway, and also it's not a station in operation where Christian is sitting, okay, so he will not do anything further, but this is otherwise a Hungarian uniform. So anyway, in railway operational research is a broad field, it has many more problems. Obviously there are excellent classical methods and heuristics, yet there is room for improvement. It's an application. We opt for conflict management, which is where you need the solution immediately, so time matters a lot. You cannot say in such a situation, so what is conflict? I'm not sure if you're familiar with train paths. This is a rather simple representation. Here's space, here's time. I'm telling this because both versions, there are versions in the railway operation where it's the opposite, the time goes from the top to the bottom. Now I'm using the planning type diagrams where the time goes to the right. Okay, and these represents trains running. So train path, it's the space-time diagram of the train. So this intercity 5320 goes like this. Starts from here with some velocity, stops at this station, waits, and proceeds. Right? Now this is a single track line, which means that the trains cannot meet on their way in the same block section because they would collide. The problem starts when the train gets delayed. Now if I introduce some delays, then if I just push in time the train paths, they will intersect here. So these two guys will collide. This is not feasible, this timetable then. The whole timetable should be redesigned in such a way that we get a feasible one, which is close to the original one. That's the goal. Obviously, I will not go into all the details of the classical literature of that. There's a huge literature. Unfortunately, even though the theory is quite elaborate, there are not so many systems around the world where this optimization is actually incorporated into the traffic management system. But I also know that for instance, in Switzerland, they have an integrated system in which they do have conflict management and they automated. And once I was talking with one of the main developers of this system, it was some 10 years ago, and he also said that they do have in the system points where they just use some very rough heuristics because simply there is not enough time to run the proper model. So indeed, if we would be able to look into these actual systems, Typically they cannot because they are proprietary and they don't tell you the details. But if we could, then we would find places where actually they fail to solve models classically. Now, ours, this is obviously just a demonstration because we had no collaboration with the producer of such a software system. We had a positive attitude from the Silesian Railways nonetheless, which is also big because at least they don't mind if you mention in the paper. In the railway companies, well, anyway, recording, I can tell them about them later. Anyway, we have finally recently published the paper. After a long struggle, this was the first version. Basically, it took 3 years to have it accepted. We also did some strategic mistakes. We can discuss them later on. Nonetheless, it now appeared, even though in entropy, I didn't want to have it in entropy, I wanted to have it in an operational research journal. Anyway, it's accepted. One thing I'm sure, this is the first ever application of quantum embedding to railway problem. And this is now acknowledged by people who are citing us. Because even before the publication, it started to be cited. And also there are not so many papers in this direction where there are actual tensor network solutions presented to such problems. So it's definitely, I regard these two as the main merits of this paper. Otherwise, these are small demonstration problems. Now we are working on a metropolitan scale problem with the DWave hybrid solver, and I strongly believe that this will be accepted in a transportation journal already. At least this is what we want to do. I just show some figures that this is a solution to such a problem obtained with DWave indeed, and this is some particular results where the red dots are non-feasible points. The tensor network solution is here. This is the best DWave solution, and it took quite some annealing time to find it. So this is about the mood of the results which are in the paper. The details are definitely in the paper. And finally, so this is these are the short-term or mid-term plans. We are working on this manuscript. Actually, right now, it's close to be finished. So, and my intention, which is closely related, and I believe we will keep on collaborating on these, I have definite interest in making benefit of tensor network in operation research. So I would like to discuss about this because I think that would be a very interesting perspective. What we are doing in particular is that with my PhD student, and this is also open for discussion, that we want to create our own hybrid solvers, and we do have certain ideas on how to use DWave as a kind of subroutine in some classical solver. We're not the only one with that, actually. So I know application papers even out which succeeded with that. And the main point in this very research direction would be, in my view, to orchestrate quantum and operational research technologies. I think that's a good last word. Unless you have some questions, of course. Thank you.
Thank you very much. Any questions? Anybody? Please,
You mentioned that briefly in your talk, but do you know any paper that or survey that would treat on at least tackle the problem of hardness of instances? Because it seems to me that this is crucial. If you come up with a solver which is hybrid, the question is how you benchmark it.
Yes.
And therefore the question is, what do you mean by the hardness of the problem? So in other words, suppose you are given a QUBO without any knowledge of the underlying optimization problem. How would you judge whether this QUBO is actually hard or not?
Very good question. I would be very happy to know. So it's always a finite chance that I'm just not enough knowledgeable to answer. But I think that it's partly an open question.
Open question,
Because as I said, I'm definitely not sure that for instance, a QUBO, which is hard to say, I do the standard linearization and observe that simplex is struggling a lot with that, or do some other linearization and I see that the cutting planes are not well behaved and so on. But I can imagine that in a tensor network setting or for DWave, it would be not that.
Have you seen any
Or vice versa.
actual study on it? Because it's a given and it's an open and challenging question, but I haven't seen that much study on it.
I haven't.
Yeah, me neither. So I think that's the
Yeah,
biggest problem.
that's and I would indeed we should elaborate on that because this is an interesting question. And even so, one thing is that there is this QUBO benchmark set, and I have the experience that the classical people prefer using this QUBO as a kind of standard, and it would be interesting to solve more of these with. And also, I just in these days, I received certain QUBOs from Janis Povach as a kind of first step of the collaboration, and he sent them with a definite intention that he would be very much interested in what we could say about them. And for sure, we started to run a few of them, and for classical solvers, they are tough indeed. This we already know. Even we can give the reasons. So actually, I would be very happy if we could run them these days. But let's return to this.
Yeah.
But this is a very important point.
So I have a very maybe simple technical question, because you said there is a relation between mixed integer programming and QUBO, yes?
Mhm.
So when you have like this integer programming, not binary variables, but they have be any integers. So is there a way to translate this D1 problem with integer programming to QUBO?
Sorry. So what I was telling that if you have a QUBO, then
You can
have a mixed
mixed
integer.
integer. So now I'm thinking about the other direction. So I have mixed
So
integer.
NMIP to QUBO. I see.
It is working.
Well,
But
Using slide variables.
but not binary variable,
I
but
don't-
general.
Well, I don't think so, because on one hand, this is an MIP of a specific structure. So we have these extra variables, and it's true there that they are considered as continuous because we want to solve very classical algorithms. But DWave, so zero, so to turn continuous variables into
That
zero.
continues,
That's
just
discrete, but integer, but
Integer you can do
but
that.
not dichotomic, not 0 1s, but
Integer you can tell.
That's doable, yeah.
Using slide variables.
but you just represent it as a binary expansion of this integer and a bunch of
In a way, yes.
Yes.
I think it's a question whether you can translate between mixed integer programming and higher orderizing, basically. So it's at the end you're gonna end up with the POTS model. It should go in both directions.
Mm-hmm. Yeah. So if you say that you assume a finite resolution on the continuous variables, then well you can try.
okay.
You can try. Actually, about that part, it has had an interesting side effect in this development of MANA, that they came up with an SDP approximate solver, which turned out to be useful in other cases. For instance, in the investigation of quantum correlations. I'm not sure if you're familiar with that topic, but if you have a Bell-type measurement situation, you want to decide if the correlations arising there can be realized with the quantum system or not, then you have to solve an infinite sequence of semi-definite programs. And they can grow big. At some point you can stop this sequence, but those programs can grow big. There are many other instances of SDP which are important in entanglement weaknesses too. And there is a paper by Janis where they are he said that essentially he didn't know in detail what this whole correlation stuff was about, but he was asked to solve these SDPs at least approximately, and he managed.
Any more questions, please? No? Okay, so let's thank the speaker again, and thank you.